Welcome to the Blue Economy CRC webinar series for 2024. My name is Professor CM Wang, and I'm the program leader of the Offshore Engineering and Technology at the Blue Economy CRC, as well as the professor in Structural Engineering at the University of Queensland, Brisbane, Australia. Firstly, on behalf of the Blue Economy CRC, I'd like to begin by acknowledging the traditional custodians of the land on which we are hosting this webinar today, and pay my respects to the elders past and present. I extend that respect to Aboriginal and Torres Strait Islanders peoples here today. Now, the Blue Economy CRC was established with a 10-year life under the Australian government CRC program in July 2019. So we are already halfway through the life of the Blue Economy in this year, 2024. We have now 43 participants from Australia and around the globe. And the purpose of the Blue Economy CRC is to perform world-class, collaborative, industry-focused research and training that underpins the growth of the blue economy through increased offshore sustainable aquaculture and renewable energy production. Now, today's webinar is about blue innovations. I'm extremely glad to have my very good friend, our speaker, Professor Jort Bouwmeester, who is not only an architect, but a great inventor. And he is from the SeaCities Lab at Griffith University in the beautiful Gold Coast area. And he conducts research on aquatic urbanism and floating marine structures. His presentation today will explore floating projects that address solutions for marine protection, provide renewable energy, and ensure food security. Now, his projects, among others, have been published in journals and books by Springer, such as the SeaCities Aquatic Urbanism and the SeaOases Floating Aquaculture for Smallholders Global Food Security. Now, without any further ado, I invite now Professor Jort Bouwmeester to make his presentation to all of us. Jort.
Thanks a lot, CM, and welcome everyone. It's a huge pleasure to have you all here in this webinar, not only as a kind of attendees in this presentation about blue innovations, but there's another pleasure because we are pre-launching from today on our floating exhibition. That's how we call it. And I wanted to show you our invitation movie, which is very, very quick, but it's already showing also what we are doing briefly. Thank you.
Welcome aboard to the SeaCities Lab exhibition. This exhibition is situated on top of an artificial reef and floats like most of our projects. The SeaCities Lab capitalizes on the ocean's efficiencies to create positive change in the world. For food security, aquaculture is more lucrative than agriculture. For clean energy and transport security, offshore islands and floating seaports are more productive. For environmental protection, floating artificial reefs and survey structures are effective solutions. And to avoid maritime conflicts, a tool to predict future developments at sea has been developed. Movies promote the implementation of our projects, while our books present the scientific background in depth. Explore more of SeaCities Lab's publications in our library, including research on urban wetland ecosystems, floating mangrove platforms, adaptive planning tools for urban seascapes, food production technologies at sea, and living islands in atoll environments. At the end of the tour, meet our interdisciplinary team of architecture, marine, structural, and environmental engineering, urban planning, marine science, and system dynamics experts. Finally, please share your comments in the guest book. Your input will help us collaborate and conquer today's challenges together. Solutions are floating and on the horizon.
So this movie is available under SeaCities.org, and it would be great if you would not just watch the movie again or forward it, but there's also the whole exhibition there. And this exhibition includes more projects than I can present today. The team of the SeaCities Lab, so that's the core team in the end, is very interdisciplinary, as already said in the movie. This is architecture, aquaculture, engineering, water engineering. I kept here an old image also with Unil in it, because Unil was in our common project, the SeaFisher, which we'll present at the end of this presentation. He was also working hardly with us and with the SeaCities Lab before he moved now to UQ to CM's team. So also welcome Unil, and thanks for everything. We are also industrial designers, structural ocean engineers, environmental engineers, and so on. And as already CM mentioned, we are publishing books. So we were launched 4 years ago. And currently we are publishing a minimum of 1 Springer Nature book per year. And we are finalizing currently the last one, or the one for 2024. And the title of that is At the Edge of the Sea, the Evolution of Amphibious Concepts. So it's all the time between land and sea. It started with land and sea level rise in the first book. And then it was about urban development solutions due to sea level rise, but then also other topics came up like global food security, and then the whole thing was changing the perspective and was looking from the sea to the land, and now we are interested in the edge of the sea and how this can be developed further. Next one, please. This is just to tell you or to show you how we think. So we were creating a brain kit. We call it a brain kit for holistic thinking, just to be sure that we are all on the same page when we talk about ecology, about systems thinking, and all the keywords. Everyone is currently using in different ways, and we were creating this programs which are explaining a deeper understanding of the different words to be not as superficial. And I won't go through all of them, but I want to show you 2 of this brain kit cards in the next slide. So the one is here. This is about innovative thinking, because we are talking today about blue innovation. And there is a methodology to innovate, and we are using that. And there's no really big trick behind it. It's just about thinking in different ways. It's the easiest is, and that's what we are doing automatically, is about optimization. So we are trying to optimize things day by day. So this doesn't need any active thinking, but the next one is already more active. That's called transfer. So you can mimic, respond, preserve, or cultivate things. And you can transfer elements from, for example, the land to the sea. And so this is creating lots of solutions. And I will show you some of them. And then there's a third one that's the most complex, where you are mixing 2 different things together. And I'm showing an application of one, which is called the SeaManta, also later, where we were mixing marine biology, coral reefs, with dive experience and a floating structure. So this is something for everyone. I'm happy to share the cards. They're also online on my own jörgbaumeister.com website. And for us, it's very, very helpful to work together in a quite structured way. The next slide is showing the other card I wanted to show, because that's how we are creating then solutions. For example, to get more food, more energy, or to deal with sea level rise. And it's very, very simple and primitive. We are just using the natural environment and built environment. There are then also subcomponents, and we are using UN definitions and so on. This is not shown in this simple diagram, but in the end, it's about the combination of experts coming from the natural environment, like geographers, marine biologists, and so on, and from the built environment, like our marine engineers, like planners, and so on. And we are combining that then also with business, because we are not only interested in this ivory tower research, we are interested in applied research. That means everything we are thinking is something we want to build. And we are now in our 4th year, as I said. So, and the SeaFisher and one other project, they are already somehow on the way. And hopefully we will be able to build the project, which will be presented at last project together with CM today. The next slide, please. So these are some of our solutions about sea level rise, survival of coral reefs, marine protection, renewable energy, food security, and evolution of the seas. And of course, I can't talk too much about everything. So therefore, I was selecting just 5 different projects. Next one, please. And we will start with the largest project, which is about the high seas, international waters, and how they could develop, how they could evolve in the future. And then the next project I will present is about marine protection, as well as the third project. The one is about marine protection of the high seas, the other one of coral reefs. And then we will end with one project, which is about food security in a smaller scale. And then we will end with the so-called SeaFisher, which is a fish pen, also related to food security. Next one, please. So these are the names. We are a little bit passionate about the sea at the very beginning, but perhaps this might be just a phase, and the names will change then later. But currently, it's very, very easy to work with these different sea names. Next one. So what will happen now is, so I will start now each of these 5 projects first with the research problem, then explaining the problem a little bit more, and then I will just come up with a potential solution. So the first is the evolution of the high seas. And as most probably everyone knows here, that almost half of the surface of the Earth is part of the high seas. I think it's about 40%. Next one, please. So everything here in red is international waters. The definition is that it's outside exclusive economic zones. And this zone lacks jurisdiction, and this allows enjoyment, of course, freedom, but also misuse by anyone. And therefore, it's very important, that's our opinion, to predict developments, to respond to necessary regulations. Next one. So this is just one example. This is in the end a normal layer or screening with GIS layers and other layers. And this is a very, very simple example where we were just putting or using one layer, which is the so-called sea mountains. These are shallow waters in international or shallow waters in international waters, and they are biodiversity hotspots. So this is the left top map, and the top right map is a kind of prediction of areas that might be or will be or already are very interesting in terms of mineral mining in the high seas. And now if we are overlay both predictions, we get the map which is shown here on the bottom. And the red areas are exactly now the areas where now the different interests of different stakeholders, the one more interested in environmental protection, the other one more in mineral mining, where they are now overlaying and they're creating potential conflicts. So this is just by overlaying different predictions using different layers. So this is I think quite logical how we are working here. And there's another example coming in the next slide. Oh yeah, this is something we will present at the World Conference Floating Solutions in Hong Kong. This is also a little advertisement for this wonderful conference. And CM is also highly involved in that. And here we will present a way how we are just also through the same tool set, different layers using or creating different hotspots. And this is now about hotspots which could be potential new countries in international waters. Or there's one terminology which is talking about sea steadings. And they would have excellent international transportation links. So there are international waters, but still very close to international airports. And they would have favorable climatic conditions. And so that would be ideal for permanent residents. So this will be presented, as I said, already December in Hong Kong. Next slide, please. And another example of this overlaying method is when we are just looking where are the top 50 container ports in the world, and where's the most container transport happening. And then we have then also, for example, depth and areas without hurricanes and other layers. If we are using that, there's indication of potential areas in international waters, so that are the dots with the E's, or in national waters, that are the dots with the N's, where we could now start with the next generation of floating seaports, which would be much more efficient in cargo operations and arrival time, which is very important just looking at the development of cargo transport. That's visible at the bottom, which changed in the last 30 years from very, very small 4,000 containers up to now 24 or more containers, 24,000, sorry, containers. So this is the next generation. We were also developing just by this method. And now the next slide, please. So and these are just some simulations. Ideally, of course, they would float in international waters, and at the same time, they would already produce energy, which could be then also used as alternative to the current energy, which is quite polluting of container ships. Yeah. So, for example, if you would transfer the energy to hydrogen, and then if you would use hydrogen transport or others. So these are simulations just showing that. And the size of this seaport would be for 8 very large container ships. Next one. So the next one is about marine protection, the next 2 projects. Can we have the next slide, please? So again, we are starting very large, global scale. And this time we are looking at this new UN Treaty of the High Seas in terms of designating 30% of international waters as marine protection areas. And of course, there are quickly coming questions up as like, where should these protection areas be established? And how should they be controlled? There's already lots of research about the first question. What we are suggesting is, again, our shallow offshore areas with less than 100-meter depth, which are called seamounts. They are hotspots of marine diversity, and out of that we could develop larger marine protection areas. And this is just now an example of different climatic zones, different ecosystems creating large protection areas. Next one, please. So, and then the other question was, how should that be controlled? And that's where we are starting to think about autonomous platforms. So this would be space frame structures that are autonomous platforms that integrate remote undersea surveillance. So there are all the different devices, elements possible, but the most obvious would be here number 7, which would be the autonomous underwater vehicle. And they could then also contact directly the bottom of this floating structure, which is shown on the right-hand side. So these are first experiments we are making in terms of how we can develop the structure further. They are not the buoyancy bodies shown. It's just about the structure. Next one, please. And so there would be, for example, a modular platform. The one I've shown you before is about 35 by 70 meter. And then that could be single point mooring or free floating structure. And then it could be also covered with aluminum to protect from other people who would like to get access to the data or manipulate the data. Of course, the Navy is also interested in this kind of thinking. And so this on the right-hand side, there's, for example, now a larger possibility for underwater surveillance platforms, which would work with 12 underwater vehicles here that could be there maintained, but also they could be charged with energy. And then there would be inside, there would be then also a maintenance platform. Next one, please. So this would be now just one example of this aluminum meshed floating structure, which would be 1 out of 15 SeaSurveyors that would allow to survey this very large marine protection areas due to the use of these autonomous vehicles. In terms of the price, we were starting with calculations, and it would be relatively inexpensive. So it would be around $450 million per year for all 15 together, including maintenance and so on, which is a fraction compared to other combined expenses of the UN. Next one. So this is now one I wanted to show you, and I will just show it a little bit quicker, because you know that already, because the movie was happening in this so-called SeaManta. And it's about, first of all, the survival of coral reefs as a research question. Next one, please. So as we know, that half of our coral reefs and associated tourism are at risk by 2035. So this is now serious World Economic Forum saying that, and the map indicates the currently existing coral reefs. So if there would be just 50% left, that would be dramatic. And of course, we can't start now to rescue this reef because there are other reasons why this change is happening. And then, therefore, it was another approach we were starting with, and that was also triggered by Angus, who is perhaps also participating today. And so he's coming from International Coastal Management Company, and he had a client in the Middle East, close to Qatar. And we started discussions how to react on this risk. And we were creating this artificial coral reef that is integrated into the marine ecosystem, but at the same time, it's also diving experience in terms of also creating some financial benefits out of that. Next one, please, and perhaps also attention and some more education purposes. So the trick here is that in the belly of this floating structure, there is enough space for electron accumulation. That's a kind of process where we're using low voltage current, and then you can grow limestone-like substances, which is ideal for the corals. And what is super important for me is all the time, because in English there is this description of being a designer. And for me, being a designer is not what we are doing. So design is just a kind of sometimes happening at the interface between different people who are all designers. Yeah, engineers are also designers, marine biologists are also designers. So, and if people now look at this perhaps a little bit unconventional shape of the SeaManta, and then people think perhaps that they were designers just making some arty design work. This is not true. So the whole design was coming up by a scientific process, including water currents, wind flows, sunlight, and sunlight again. The second sunlight was then responsible for extending the underwater reef, so the belly, to get more sunlight. And that's the reason why this shape evolved, which is a little bit manta-like, and therefore we were coming up with the SeaManta name. Next one, please. Yes, so there are different functions, of course. There is the exhibition as seen in the video. There's also very important a breeding aquarium to create a whole ecosystem around the corals, an event space we were using for the exhibition, but there are also different underwater displays. And the height of them is dependent on the different dive licenses. And of course, there's the artificial coral reef integrated in the belly. Next one. So this is just an interior shot. And in the end, ideally, it would be not just to enjoy an artificial reef and to create a dive experience, but it would also help then to settle more heat-resistant corals. So it could be also an outpost for that. Next one, please. So this is now the second last project, which is about food security. And so we were very, very interested in how to solve problems which are related to food security on a smallholder scale also. So it's about availability, access, utilization, and stability. Can I have the next one, please? So if you look here on the map on the left-hand side, and then at the hunger index, and then you see there are lots of countries who have alarming hunger, then serious and moderate. And the reason for that, or one of the reasons for that, is that although the population growth has been doubled or not the growth, but the amount of people living on the planet has doubled between 1970 and 2050, or even more than that. The supply of cropland is still the same. So therefore, there's a growing lack of cropland. And knowing that aquaculture is more efficient than agriculture, we were very much interested in the question, how can we now think about something which has to do with aquaculture for smallholders? So it should be also very, very affordable. And I lived for 3 years in Africa. So I know some methods how to produce success, for example, and one of the success stories is related to using tractor tires, the inner tubes, because you can create lots of stabilities with that, and you can fill them either with water or with air, and build out of that together with membranes and other elements which are also very, very cheap. We were coming up with a kind of a potential construction of different units. Next, please. And we were creating the SeaOases as a self-contained closed-loop floating farming system. I will show you in the next slide how it works. Designed to empower smallholders in developing countries. It enables them to cultivate high-value cash crops for international markets, while also producing fuel and food crops for local consumption. So in the end, you are creating businesses, but at the same time, you are also providing food for these people. And how this tractor tires system works is shown on the right-hand side in the example of a hydroponic unit. So there's the base unit, and then there's a rope and buoy system connected to that. And there are historic examples which are related to this kind of cultivation. For example, the floating garden dub systems in Bangladesh, which could be then also transferred here. Next one. So this is now how the different units could work together. So there is a hydroponic unit, a mixing unit, a filter unit, but then also there's a pump unit, a fish algae unit, and they can be combined in different ways, and they can also farm different species. So the combination and of different units and their different configurations is related to the different climatic conditions. So sometimes you can grow the one species better and the other not, as we know all. And so it's also about water temperature and. So in the end, it's a flexible system, and a system for one family would be around $100,000, and there would be a return of investment after 1.5 to 3 years. And in general, it should be very, very interesting for investors, because the whole market for food crops will grow up to $5 trillion US. This is coming from the World Bank. And there wouldn't be any need for extra land and fresh water. Next one, please. So now we are coming to the project. I have 1 minute, CM. I will need 2 perhaps, yeah. Next slide, please. So this is now a pure Blue Economy project. I was leading the first phase, and then CM's team is taking over the second phase as the general leader, but we are still highly involved. And the research problem here is mainly about increasing fish farming and pushing operations offshore, resulting in construction of large and costly steel structures. So we had our research questions around greater flexibility, less material price, and lower material consumption. And I'm just showing you now here how it works with the modularity. So we were coming up with a modular system, which is very flexible and which can be prefabricated. Next one, please. So then we were using, and that's quite new, HDPE as a load-bearing material because it's affordable, recyclable, and there are lots of other additional advantages. And CM will talk about that in depth. Then the third reaction is that we are submersing the whole structure in case of storm events up to around 20 meters. Next one, please. So, and this is now from phase 1, still the first experiments demonstrating the advantages of submerging the structure and the different forces there. We filed also one patent for that structure. And in the end, we were also starting to calculate, and currently we think that we can reduce the normal expenses by 3/4 to 6 million plus mooring then of 2 million. I think that's it. Next one, please. So yes, so we know, and that's the reason why I'm here and also CM. So it's a significant project. We are now in phase 2. We hope we will realize that further because, and now on the right-hand side that selects the last slide, this is also one of these brain kit cards. This is just showing how processes are working. And we are now just in the first circle, and we want to go up the whole spiral until commercialization, which is also the aim of the Blue Economy CRC. Thanks a lot. Next slide, please. Please remember, if you are interested, just watch on seacities.org. Other projects, perhaps the movie again, if you liked it, and get in contact with us if you want. Thanks a lot.
Thank you so much, Jort, for a very nice sharing of all your very interesting projects. So I'm taking over for the next 5 minutes to mention about the SeaFisher, a little bit more details for you guys. You know, the SeaFisher is a very, very interesting concept that came through what Jort mentioned about using 3 phases, optimizing, transfer, as well as fusion to come up with this design. And it is through a lot of hard work, scouring through the literature for the best form of structure, materials, and strategy to be able to make the fish pen survive during a storm, as well as to keep the fish healthy and growing well. So this is the SeaFisher the fact sheet here. I think the main thing is key feature is that it is a submersible type of fish pen. There's one submersible fish pen that is has been in operation for 17 years, and that is in the Mediterranean Sea. It's called the Subflex, designed by Nital Dreamer, who is from a professor in Technion University. But when we study the design, it's a bit more flexible than we imagined. So it may not be suitable for our Australian waters. So I had to make it a little bit more rigid. So now we are using the material that chosen for this SeaFisher is high density polyethylene. But as you know, this material is very light. It's lighter than seawater. So in fact, all the pipes inside this HDB pipes are filled with seawater, and those at the bottom of the SeaFisher, the pipes are filled with sand to bring the center of gravity low. And the novelty is that instead of one single pipe, we are using a bundle of pipes. The bundle of pipes is superior, and it gives a lot of not only you know, the strength and stiffness that required, but also provide a lot of redundancy. We are designing this SeaFisher to be able to withstand a wave height of 8 meters and a wave period of 12 seconds, which is typical of that in Storm Bay in Tasmania. And the current speed is very high at 0.8 meter per second. This is modular, but the one we are looking at is a 2x6 array of cubic cages of 20 meters in width, diameter, width, height, and as well as length. So it's a cube, and when assembled together, they can give you a cage volume of 96,000 meter cube, which we can farm almost about 300,000 salmon fish. So it has a feature of a single board mooring system, so that it allows you to weather vane and be able to reduce the environmental forces on the fish pen. Not only that, it allows you to spread the waste over a much more wider sea space, making it much more better in terms of waste dispersal. The estimated cost, 6 million with the fish pen, but 2 million for the mooring system. Might be a little bit more depending on where it's being constructed. And I will show you a little bit more about the special feature of the SeaFisher. But Leslie, can we turn to the next slide? We'll show you a short video of the SeaFisher first. Yeah. Thank you. That's thanks to SeaCities, the Professor Yot Baumeister, as well as his team, especially Martin, who did the video. So thank you so much for providing us a visual display of SeaFisher. Now, that brings us to TRL around 3. The conceptual design is completed in phase 1. Moving to phase 2, we are going into doing some experimental tests and refining the design a little bit more. So here is show you a picture of the a much more detailed design of this SeaFisher. We have now introduced ballasting tanks, and these ballasting tanks are vertical vertical ballast tanks made of aluminum to be able to let the SeaFisher descend to appropriate depth and be raised to the surface as and when the rough waves have come down over after the storm. The key point here is that because the SeaFisher is made of bundles of HDPE pipes, it's still very flexible. We need to stiffen it up by using glass fiber reinforced rods in a die grid, arranged in a die grid fashion. That will really stiffen up, and that's the key to making it work. If you remove this die grid glass fiber reinforced polymer, the whole thing will break out. The whole SeaFisher will not be able to take the wave forces in an offshore site. Next slide, please. Okay, so the net that we are using is Kiko net. I would regard as one of the best because it's been used in the Ocean Farm 1. As you know, the Ocean Farm 1 is one of the earliest offshore fish pen designed by the Norwegians, now trialed in the Trondheim waters in Norway. And they use Kiko net. They have gone through 1-year cycle of operation, and the KikoNet performs superbly with no problem in biofouling, as well as in terms of ability to resist the environmental loads. The tear due to the KikoNet is due to human errors, nothing to do with environmental loads. So this gives us confidence that we are moving the right path to adopt the KikoNet for the SeaFisher. Next, please. You can see more details into the SeaFisher design. We have the pipe bundling system, connector system. The connector not only holds the pipes together, but you can imagine they are like ring stiffener. They stiffen up the the HDB pipes as well, and to reduce the contact surfaces of the bundles of pipe. We are thinking of putting textile materials of some kind that will give a lower the surface area to prevent biofouling, because biofouling is one of the critical problems or issue that we are always grappling with. So this solution, where we wrap this up, the pipes, with textile, and either use Velcro or using some zip mechanism, we can always remove and detach, and for cleaning purposes and so on. Next slide, please. So this is the ballasting system, the vertical ballasting tanks made from aluminum to allow the compressed air to bubble up, or also to be removed, as to allow the SeaFisher to descend or refloat, as the case may be. Next slide, please. No, I think we are going backwards, right? Next slide. No, we're going backwards. Forward, one more. Yeah, so this shows a hydroelastic analysis of the SeaFisher at the surface, and also at 20 meters. You can see that the contraction of the water cultured volume, if the SeaFisher remains on the surface while we have a strong waves, is, although the SeaFisher can survive, but the fish will be put into a state of stress, because most of the fish will dive down to the bottom of the SeaFisher, resulting in a stampede of fish. But once it's lowered down, we have a much calmer environment, and there's no reduction in the water culture volume. So this will safeguard not only the structural integrity, but also the well-being of the fish. And then once the storm has passed by, we will refloat it back to the surface. Okay, that's all I want to say about the SeaFisher. I want to give the opportunity to all of you. I know there's many of you out there, but we'll try to answer as many questions as possible. And so please send your questions through the Q&A tab. Okay, so any questions? Okay, here's a two-part question, Dean Filford to Jort. How will coral reefs thrive cast in the shadow of the SeaManta structure? Will the corals be upside down, so as to speak, or will there be some kind of artificial iron-based substrate that favors biorock type electro accumulation?
Where's the second phase, or was it just one question now?
That's one. The second question is the second
Okay.
part. The second part of the question is, that said, with a successful reef bed established, how would the structure be designed to reduce biofouling, ongoing maintenance costs, given many restoration projects?
Oh,
yeah.
Okay. So the first question, so that's the reason why, and we were developing that with our colleagues from marine engineering together. So in the end, that was the reason why we were shaping this structure in a way that we cut in the center this long opening that allows the corals growing on the right and left hand side of this edge. And then the other reason was that we had the wings developed so that we have even more sun irradiation and sunlight coming, penetrating the structure outside. So that was the reason for the whole shape. And wherever it's less solar irradiation, we can use that to produce this kind of caves and different marine ecological structures, which are allowing different elements of the whole ecosystem also to live together with the corals. Yeah, so you have to create a whole. It's not just about an artificial reef. It's for corals. It's about a complete artificial ecosystem. And so therefore you have also to allow other species also to be part of this ecosystem. And so that was the reason why we were using also other elements, and this electroaccumulation is a kind of a way how we can produce then this substance, which allows now, it's almost like a rock substance, which allows the whole ecosystem to somehow attach to it.
Okay, thank you so much. There's another question.
And if it's about biofouling, if that was the other question, if it's
the
about
biofouling.
SeaManta biofouling, so biofouling is for me quite a word which is so negative connotated, yeah. So that it fouls, biology fouls. Of course, it's we can also say it's the environment which is growing there, yeah. So ideally, the ecosystem would deal with elements which would grow too fast by themselves. So it would be self-balancing, and therefore there wouldn't be any biofouling. Just there would be food for the whole ecosystem, just to create it further and further.
Brian added to your answer. He says that the corals could actually survive better in the shade, less photo bleaching in the summer. So it could be advantageous. I mean,
Yeah,
you
it
don't have
depends
to be
which
fully honest.
corals, and they like also not a complete darkness. Yeah, so you have to get the right irradiation and the right species together also. Yeah, so
yes, you're right.
Yeah.
Some of them are tropical corals and some of the temperate.
Yeah.
Okay. There's from Brian Van Hossen, say which portions of SeaFisher are made of FRP or other fiber reinforcing. I think I can answer this one. The SeaFisher, of course, the structural members are made of HDPE pipes, but we have also a die-grid kind of stiffness that runs 45 degrees to each other, and at the outer attached to the outer side of the FRP pipes, those are glass fiber reinforced polymers. Okay, so that's the answer to that question. Martin Note asks you, could your floating mechanism be used to generate ocean energy by converting potential into hydraulic energy?
Which one? Yes, of course, in general, yes. And I know there are other groups working on this kind of energy converters from wave energy to electric energy, and of course that's fantastic. This is not my competence. I'm a little bit interested, and therefore I'm also interested in SciTech here, in what is happening in terms of the development of floating wind turbines and so on. So, but the wave energy transformers, this is fantastic, and I've seen some prototypes. So yes, the answer is of course yes, that would be fantastic.
Now, Jort, can I ask whether this SeaManta have reached the stage whereby some clients will be interested to have it built off the coast of
So there was someone interested, and then I don't know what is the current state of these discussions. It would be fantastic. We were trying to launch it also for the World Championship, Soccer World Championship, because it would be also a good event space, and then we could use afterwards it to grow corals. But I think we were coming too late, so we are still looking for an application. It would be not very expensive, and the construction is quite easy as all our projects. So if someone knows someone or if an industry, I know there are also lots of industry people there. If there's a possibility to go one step further, that would be in the end wonderful. Perhaps I take that also this opportunity to thank not only Macaferi, but also Juan and Tassal and Akru, who are huge supporters of our projects. And it would be great if you could stay on board, and perhaps others could also go come on board, either on the SeaFisher project or also on other projects.
Thank you so much. Now, hang on, there's another question that came through. Let me have a look. Can SeaManta withstand tropical cyclone conditions?
No, the SeaManta is just for the Arabian Sea, nothing, or Arabian Gulf. Some call it also Persian Gulf. So it's just for this environmental conditions. So it's there's once a year in average there's a storm, and then we have sometimes this events like we had now in Dubai. But normally it's very quiet there, and therefore, as soon as it would be in another environmental condition, it would look completely differently. Yeah, so no, the answer is no, not at all.
Okay. Yeah, I think that's about the time that we have for this webinar. First of all, thank you very much, Yot, for your time and your making this presentation and creating those beautiful slides for us. By the way, this webinar is recorded and will be made available in the coming days for you guys. You can also check out the Blue Economy CRC events page for any upcoming webinars and events. So I just want to thank all the participants of this webinar. And also, Leslie, thank you so much also for helping us with the recording and also with the organization of the webinar. So with this note, thank you very much and have a pleasant day. And we'll see you again in the next webinar. Thank you.
Thanks a lot for the opportunity.